Hello, this is Sabir. The topic of our discussion in this video tutorial is algebraic limit theorem. What is a algebraic limit theorem? Here is the statement of this theorem. If you have a two sequence an and bn, the sequence an is converges to a and the sequence bn is converges to b, then the followings are true. That is, the limit of the sequence Cn, the scalar multiplication by C to the sequence An is equal to Ca, or in other word, the scalar multiplication of C by A. Then the limit of the sum of the two sequence is equal to the sum of their limit. And similarly, the limit of the product of two sequence is equal to the limit of their product. And same is true for the division also. The limit of the division of two sequence is equal to the division of their element, provided b is not equal to 0. You must have seen these properties of the sequence in your calculus course, but here we will prove these property by using the definition of convergence of a sequence. Let's get started. I will prove this part one by one. So first I will prove that if the limit of the sequence an is equal to a, then the limit of the sequence can is equal to ca for all real number c belongs to R. Now let's begin with the proof. So first thing we can observe without any loss of generality, I can assume C is not equal to 0, because if C is equal to 0, there is nothing to prove, because this side will become 0 and this side will become 0, and 0 sequence is always converges to 0. The next is I will write down what is given and what I need to show. So the given is the sequence an converges to A. This is given. And I would like to show, want to show that the sequence C time an is converges to Ca. So this is I would like to show. And since this is a given, so this implies what I have is for all epsilon positive, there exists a natural number n, which is belong to the set of natural numbers, so that the difference of an minus a is less than epsilon when n is bigger than or equal to that capital N. So this is a given. And this is what I want to show. So I will do some scratch work here. What I would like to show, I would like to show C time an minus Ca is less than epsilon when n is bigger than or some capital N, and this N I need to find. I need to find N so that this inequality is true. And I can do some manipulation of this this inequality, which is on the this term, which is on the left hand side. So C time an minus Ca, which can be written as absolute value of C and an minus A. Here I use this property, the absolute value of two real number. The product of the absolute value of the two real number is the product of their absolute value. So as now you can see here, if I want to make this quantity less than epsilon, all I need to do is I need to make this quantity an minus a less than epsilon divided by absolute value of c. That's I need to do. So since I already have, I have that for any choice of epsilon, this quantity is less than epsilon. So I can take here, take my epsilon this time, epsilon divided by absolute value of c. Because this is a true for any epsilon, so this will be true for this epsilon. So this implies for this epsilon, because I take one epsilon here, so there will be exist again a natural number. I'm gonna stay with the same natural number. And this implies an minus a is less than is equal to epsilon divided by absolute value of C when n is bigger than or equal to n. So I already have that n. So in order to prove my result, I'm going to use that same n. So what I need to do is, as you can see that for all epsilon greater than 0, there exists n. I'm going to use the same n which I have, which is given, so that now I need to show so that when n is bigger than or is equal to capital N, this should implies this term C time an minus Ca. I need to show this term is strictly less than epsilon. But as you can see that this term can be written as C time absolute value of an minus a. But we already have here that when n is bigger than this capital N, this quantity is less than epsilon over C, absolute value of C. So this implies this is a less than absolute value of C, and this is a epsilon divided by absolute value of C. And this absolute value will cancel out and I will get epsilon. And this is true for n strictly bigger than capital N. So this proves the first property of our limit, that the limit of CAN is equal to CA. So this completes the proof of this theorem. Next, we will prove the second part of our theorem, which says that the sequence AN plus BN converges to A plus B. So first I will start with what is a given. So we have the sequence AN converges to A, and also we have the sequence BN converges to B. This is a given statement. And what I want to show the sequence AN plus BN, the sequence converges to A plus B. This is I want to show. So let's start what is a given. If a sequence AN is converges to A, it means for all epsilon positive, there exists a natural number. I'm going to call this time N1 is a natural number. And so that the difference AN minus A is less than epsilon when n is bigger than or is equal to N1. So n is bigger than or is equal to N1. Similarly, this implies for all epsilon positive, there exists a natural number. This time I'm going to call N2. This belongs to the set of natural number such that, this is a symbol of so that the Bn minus B, this is a less than epsilon when n is bigger than or is equal to N2. So these are the two statements which are given. Again, I'm going to do some scratch work here before I jump into the proof. So my scratch work is, in the scratch work, I would like to show this AN plus BN minus A plus B. This quantity is less than epsilon when n is bigger than some natural number n. And we want to find this n so that this inequality is whole. In a similar manner, I'm going to take this quantity and manipulate it. So AN plus BN, this is a minus A minus B. This also can be written as AN minus A plus BN minus B. And we know the triangle inequality. So if you have a two real number x plus y, this absolute value of this real number is a x, the absolute value of y. So I'm going to write this one is less than is equal to absolute value of AN minus A plus the absolute value of BN minus B. And we have given this is a less than epsilon already when n is bigger than the N1. And this is also less than epsilon when n is bigger than n2. So here, if I choose my n bigger than n1 and n2, this will become less than 2 epsilon. So actually, this will become less than 2 epsilon when if I choose n is bigger than n1 and n2, because for that values of little n, the both of this inequality will hold. So now this gives me an idea that what I need to choose my n and how I can make this is equal to less than epsilon also. So I'm gonna do a little bit modifications in my given term, because since this is a given for all epsilon, I can also, this is a true for epsilon divided by 2, and that is also true by epsilon divided by 2, and I can just do that because since the sequence an is converges to a, and this statement is true for all epsilon, so I choose my epsilon is epsilon divided by 2. Now I can basically choose my n here, or I can write down the proof actually. So for epsilon positive, there exists n. So this n I'm going to choose is the max of n1 and n2. Then, as you can see that if I choose my little n bigger than that capital N, but capital N is the maximum of n1 and n2, so this will say that n is bigger than is equal to n1 and n is also greater than or is equal to n2. That the two inequalities will hold. And then I can show the difference of an plus bn minus a plus b. This is nothing but this is equal to an minus a plus bn minus b. And then I will use the triangular inequality. This is a an minus a plus bn minus b. Since n is bigger than n1 and n2, it means this statement hold and that statement hold, or in other words, this inequality hold and this inequality hold. Therefore, this is less than epsilon divided by 2 plus epsilon divided by 2, which is equal to epsilon. So this completes the proof. This implies an plus bn sequence converges to a plus b by definition. Next, we will prove the third part of the theorem, which says that the limit of the product of two sequences is equal to product of their limit. Again, similar manner, we're gonna start basically what is given. So given is sequence an converges to a. Also the sequence bn converges to b. So this is a given. If the sequence an converges to a, this implies for all epsilon positive, there exists natural number n1. So I can choose the natural number n1 belongs to set of natural number, so that the difference of an minus a is less than epsilon when n is bigger than or equal to capital N. Similarly, I will write the definition for the second sequence. Now I will write down what I want to show. I want to show that a n b n converges to a b. I want to show that the sequence a b n converges to a b. And again, I'm going to start doing some scratch work. What I need to show is a n b n minus a b. This is, I want to make this is a less than epsilon when n is bigger than capital N. So I need to find this capital N so that this inequality hold. Again, I'm gonna take the left-hand side and start doing some manipulation. So an, bn minus ab. I'm going to write this term as now an, bn. I'm gonna add a term a and b, and also I have to subtract it, a and b, and then have minus ab. So I add an extra term a and b, and I also subtract it, or in other words, I'm just adding 0. Now I'm gonna combine few terms. So I'm gonna combine a and b. This will be combined with this. So if I combine, I can pull out a n, and this is a b n minus b. And then I'm gonna combine this one. I can pull out b from here also. This is b a n minus a. Now I will use the triangle inequality. So this will be less than is equal to a n, b n minus b, and this will be equal to b, absolute value of b. This is a n minus. Now, since my goal is to make this whole entire thing less than epsilon, and I know that this quantity is less than epsilon and this quantity is less than epsilon, and that is true for all epsilon. So in order to do that, what I sort of have to do if I want to make this whole entire less than is epsilon, I'm gonna make this an less than some number capital M, and bn I will basically make epsilon over that capital M, and here I'm gonna put 2 also, and this is a bn, and this quantity I need to make less than epsilon divided by 2 absolute value of b. And as you can see, I can make bn minus b less than epsilon when is bigger than n1, and I can also make an minus a less than epsilon when n is bigger than n1. So therefore, this can be, I can make this when n is bigger than or equal to n1 and n2. There is a comma. So next, what we're gonna do is we're gonna modify what is given, because the given quantity are true for all epsilon. So I'm gonna take a particular epsilon, which is a epsilon divided by 2m, and therefore this will be true for epsilon divided by 2m when n is bigger than n2. And this one similarly I can make this one is absolute value of b. So this will be a true for epsilon divided by absolute values of b, because these statement they are true for all values of epsilon. So I choose the epsilon now, epsilon divided by b and epsilon divided by 2m. So now there is one more thing which we use here. We are saying that the absolute value of an can be less than is equal to m. Why this is true? Why the absolute value of the number we can make less than some real number m? So this is true because we have one theorem last time. Since the sequence an is convergent, so the theorem implies every convergent sequence is bounded. So therefore an is also bounded. So if the sequence is bounded, it implies there exists a real number m, which is a positive. This implies an minus. So an is strictly less than or is equal to m for all values of n. And this is true for all values of n. It's not just true for when n is bigger than n1 or n2, it's true for all values of n. So now we have, basically we have this inequality, we have this inequality, and also we have this inequality. And this inequality is true for all values of n. And I think after having these inequality, I can write down the proof. So let's begin the proof now. So here for all epsilon, for epsilon positive, there exists, I can now choose my n. So again, my n will be the max of, because this is a less than this inequality, and that inequality is only true for when n is bigger than n1 and n2. So I will choose my n, the max of n1 and n2. Then when n is bigger than is equal to that capital N, this implies n is a bigger than or is equal to n1 and also n2, because n is the maximum of n1 and n2. And therefore, if this is a true, then the sequence an, this term an bn minus ab, and as you can see this manipulation, I'm going to just write down this calculation again, you know. So this, according to this manipulation, so with this term is a less than is equal to an bn minus b plus absolute value of b an minus c. And this is a less than m, so this is a less than m, and this is a less than epsilon divided by 2m, because n is bigger than n2, and this is just a b, does not depend on n, and this quantity is less than epsilon divided by 2b, so I need actually 2b. And if you simplify this thing, this is just less than epsilon. So this completes the proof, because I able to find n so that this quantity is less than epsilon. So this completed the theorems, or in other words, the sequence an time bn, it converges to the limit a, b by definition of convergence of sequence. Now, next to prove the last and the fourth part of our theorem, which says that the limit of the sequence an divided by the bn is equal to an divided over bn. So I'm going to start the proof of this little observation. So proof. So limit n approaches to infinity of an divided over bn. This also can be written as limit n approaches to infinity an times 1 over bn. So I can write this sequence, the quotient as a an times 1 over bn. But we have already proved that the limit of the product is the product of the limit. So this property, the property number 3 of this theorem, will say that this will be a limit an time a limit n approaches to infinity of 1 over bn. So this limit is this limit, this is equal to a. And if I can show that this limit is approaching to 1 over b, then I will have the result of my theorem that the limit of the sequence an over bn is equal to a divided over b. So actually what I need to show, we need to prove or show the sequence 1 over bn is converges to 1 over b. So this will be the sufficient to prove that if the sequence 1 over bn converges to b, then by using the property 3, we can prove that the sequence an divided over bn converges to a over b. So now let's begin what we have. So again, we're going to start from given. The sequence bn converges to b. This is a given. So if this is a given, it means for all epsilon strictly positive, there exists a natural number. I'm going to call that natural number n1 this time, and you will see why later on. And so that the bn minus b is less than epsilon when n is bigger than or equal to n1. This side. Now I'm going to do some scratch work before I further proceed with the proof. So what I basically would like to show is 1 over bn minus 1 over b. This I want to make this sum less than epsilon for any given epsilon when n is bigger than some capital N. So this is my goal is. Again, I'm going to start calculating the left hand side and do some manipulations. And this is basically, if I make the same denominator, this will be absolute value of b minus bn divided by the absolute value of b and b. And this I can write 1 over absolute value of bn, 1 over absolute value of b, and this is a bn minus b. The b minus bn is the same as bn minus b if they are inside the absolute value. So I already know this is a less than epsilon, and this is just a constant. I can just basically make this less than epsilon time b. So that will basically kill that constant. But I need to find also what is the limit of this sequence 1 over bn. So like I need to also find some of sort of this is less than or equal to some real number or less than some epsilon. So let's work to produce this term 1 over bn. So first I'm going to take again from the definition, I'm going to take the epsilon this time, b absolute value of b divided by 2. And you will see in the later on why I choose that epsilon is equal to b divided by 2. So for that epsilon, because this statement is true for all epsilon, when the sequence bn is converges to b, this statement is true for all epsilon. So I take this epsilon, so it means corresponding to this epsilon, there will exist a natural number n2, I'm going to call n2 this time, which is belong to set of natural numbers so that bn minus b less than absolute value of b divided by 2, and this is a true when n is bigger than or is equal to n2. So now let's start with again, this is bn because this is what we need to compute. And we need to compute 1 over bn. So I'm going to start for bn and then I will compute the reciprocal of that. So here I'm going to do again a manipulation. I'm going to add a b and I'm going to subtract a b. And then I will use this very important property of the absolute value, x plus y, the absolute value of x plus y is greater than or is equal to the absolute value of x minus absolute value of y. So this is another property of the absolute value of the sum of two real number, which is another triangular inequality. So if I use that triangular inequality here, so first let me rearrange it. So this is a b and this is a plus b n minus b, and this will be greater than or is equal to absolute value of b minus absolute value of b n minus b. Now since this quantity bn minus b is a less than absolute value of b divided by 2, so if I multiply negative sign on both sides, this inequality will flip. So if I multiply negative on both sides, this inequality will be minus b strictly greater than. So if I put a negative sign here, this inequality will become, instead of less than, it will become greater than minus square root of b divided by 2. So if I use this one here, so it will be strictly absolute value of b minus absolute value of b divided by 2. Therefore, this is equal to absolute value of b divided by 2. So now let me summarize what is we get from here. I get b absolute value of b n is bigger than absolute value of b divided by 2, or in other words, this is a true when n is bigger than n2, or in other words, this is a 1 over absolute value of bn is less than 2 divided over b, and that is true when n is bigger than n2. So now I'm gonna basically circle my two main inequality. This is a first inequality, and that and this one also. Now let's go back to our scratch work again. So as you can see in this scratch work, I have 1 over b is, this is a strictly less than 2 over absolute value of b now. This is just 1 over b. And if I can make this quantity now, if I can make this quantity epsilon time b square divided by 2, then whole entire thing will be is equal to epsilon. Since this is a true for when n is bigger than is equal to n2, and this I can make true for when n is bigger than is equal to n1, and therefore this will be true for when n is bigger than is equal to n1 and n2. And how to do this? So all I can do, because this is a true for all epsilon, so I'm gonna change that 1 to b. Instead of this, I'm gonna multiply that epsilon absolute value of b squared divided by 2. Since this is a true for all epsilon, it will be true for this epsilon. So this will be b absolute value of b squared divided by 2. So now I can start my proof. So let me first make some space. So now I can start writing down my proof. I'm going to start writing down my proof here. So for epsilon positive, there exists n. Again, I'm going to choose n as the max of n1 and n2. And then when n is bigger than is equal to n, it implies n is bigger than is equal to n1 and n2. And this implies, so this quantity now 1 over bn minus 1 over b. So if I write down this calculation from here to here, right, this is equal to 1 over bn, 1 over b, and this is a bn minus b. Since n is bigger than n1 and n2, it means this inequality hold and this inequality hold. So these both inequality hold. So therefore, this is therefore this is equal to 2 over absolute value of b. This is a 1 over b, and this is a epsilon b squared divided by 2. And this is a whole entire thing is equal to epsilon when n is bigger than n1. So this completes the proof of this theorem that 1 over b converges to 1 over b. So as you can see that in the very beginning of the this proof, I show you that if an and bn can be written as an over 1 over bn. Therefore, this converges to A, and then this converges to 1 over B. So this implies A converges to AB, or in other words, AN over BN converges to A over B. So this completes the proof of our this last part of the theorem. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.